Thanks, Andy. So I guess I'll start off with this is the epicenter for the Petermann Ranges earthquake. It occurred on May 26th of last year. I was at the Batlow Cider Festival when it happened, getting quite drunk at 10 a.m. in the morning. But you're never able to hide from the seismologists here, so I got a phone call that said, "How soon can you be back at work? Because we need you to go out to the desert." But just as an introduction to this earthquake, magnitude 6.1 was the largest earthquake we've had in continental Australia since the 1997 Collier Bay earthquake. As Andy said, there were no injuries or damage to the built environment caused by this earthquake just because of its remote location. But the energy release from this earthquake was 11 times the energy release from the 1989 Newcastle earthquake, which took 13 lives. And coincidentally, it's about the same energy release as one North Korean hydrogen bomb. So it's actually an enormous event that we were just fortunate that happened in a remote location. And that seems to be the modus operandi for Australian earthquakes, in that our populations are very concentrated, so if you were to put an earthquake somewhere in Australia, you're probably not going to hit population. So this is a zoom in of the location of the earthquake. This is what we knew a few hours after the event, that we had Katajuda and Uluru here. We had a epicentral estimate with a 10 to 20 kilometre uncertainty ellipse around it. This is the focal mechanism, which indicates it was a thrust event. And Google Earth told me that we had a kind of dubious dirt track going out past the epicentral location. Now, I was employed 16 years ago in GA to tell the seismologists why earthquakes happen where they do. And this was potential gold, in that the Woodruff thrust actually intersects that uncertainty ellipse. And if there's any candidate for where you'd like to have a large earthquake, the Woodruff thrust is it. There's a 30 kilometre displacement on the mantle across that fault system, which you would expect would concentrate stress of some sort. So at this point, I was excited that I was going to go out to the desert and find a surface rupture on the Woodruff thrust, which is a 1,000 kilometre long fault system. From the seismologist point of view, these large events are very important in that we can collect data by putting out an aftershock seismometer network. We can collect ground motion data, which can inform earth models and actually give us better earthquake locations and magnitudes, and hence better hazard assessments in the future. So that was the primary task of going out in the field, was put out seismographs. The surface rupture was also an exciting possibility. In 2012, a much smaller 5.4 earthquake, 250 kilometres to the southeast at Ernabella, ruptured the surface. And we can get so much more information when we can actually tie a subsurface geophysical entity, i.e. the earthquake hypercenter, to some surface features like deformation effects on the surface, the height of any scarp that formed, and the length of any scarp that formed. And using that data, we can calibrate scaling relations to say, this size earthquake gives us this long scarp, which is this high, and then I can go back to my paleo earthquake record of fault scarps and assign magnitudes to those events, and that feeds into the hazard assessment process. So out we went to the field. Within 2 days of the earthquake event, Craig Bugden and I had put out 4 seismographs along that one dirt track, which is actually a pretty good effort given how remote the location is. The next morning we downloaded some of that data and did some rough locations of the earthquake, and we were able to refine our network of seismographs to basically, we were looking for an azimuthal coverage around the earthquake and one over the top to give good depth estimates. And it turned out that the GA estimate, even though it has a large uncertainty, was pretty much bang on the spot. Within 2 weeks, collaborators at the ANU and the University of Melbourne had put out some more seismographs. So by this stage, 2 weeks after the event, we had about 16 instruments recording aftershocks. And I'll show you later, this allowed us to, as compared to this uncertainty ellipse of 10 to 20 kilometres for the initial event, we were recording aftershocks with an uncertainty of 200 metres. So that's pretty amazing for an intraplate area. Like Japan and New Zealand can do that, but we usually can't. As for the surface rupture, this picture up in the right shows where the Woodruff thrust surface trace is mapped to cross the immature track. There was no surface rupture and the camel wasn't talking, so that was a bit disappointing. Craig and I were able, however, to map some cracking in that track, and paradoxically the cracking intensity was increasing towards the south and southwest, which didn't really fit with a Woodruff thrust rupture, because the intensity should kind of increase towards where any surface rupture would be. But we'd kind of driven all the tracks and it was trackless desert elsewhere, and so we'd kind of exhausted our possibilities there. But we still had the seismograph network, so we were still going to learn something about this earthquake. So we went back to the office, and after 2 weeks we started getting INSAR interferograms coming back. And it turned out that it wasn't the Woodruff thrust that ruptured. This is a pulsar interferogram that Sarah Laurie put together with the unwrapped over the wrapped image. This is basically showing that the colour fringes show deformation in the line of sight towards the satellite, with the satellite being somewhere up near the where the focal mechanism is. But this is telling us we have a northeast dipping rupture that probably links into the Woodruff thrust rather than the Woodruff thrust actually having ruptured. And the cracking that Craig and I saw on the road was the far distal northwest end of that rupture. So had we walked 5 kilometres out to the east into the trackless desert, for no reason at that time, we would have found whatever this INSAR was showing us. So to give you a bit better idea of what that INSAR picture is showing you, I'll put some section lines through that. So each fringe at the pulsar wavelength is about 12.5 centimetres of deformation. So between the pink and the pink is 12.5 centimetres of line of sight deformation towards the satellite. If I assume that's vertical, I can count these fringes up and get a deformation at the deformation front, and it's up to 0.9 metres with an average of 0.8 metres over an 11 kilometre section in the centre of the feature. I guess surprisingly in the first instance is the scaling relationships developed between earthquake rupture length and magnitude suggest that this event should have made a 10 to 12 kilometre long scarp. But this thing's 20 kilometres long, so we're learning something already, that our scaling relationships need calibration. As is the case with most reverse surface ruptures, it was not just all up on the hanging wall side. There was actually about 0.7 metres of up on the hanging wall side and 0.1 metres of down, so a footwall subsidence on the southwest side of that event. So that became important in the later field work as well. So we went back out in the field to see if we could actually see on the ground what this pulsar interferogram was telling us. We went out with an RTK GPS with the idea of mapping the position of any scarp and the vertical displacement along that scarp. University of Melbourne also wanted to put out another seismograph to improve the azimuthal coverage of our network, so we were able to get a helicopter and put that out, which ended up being fantastic, and we downloaded the seismographs. Now, a slight logistic issue here is that June of 2016 was very wet in the central Australian desert. The ground was saturated when we went out there, so any further rain would have made it a bit difficult to get out along that track, so that was something we had to be aware of. So this is the seismograph we put out about 10 kilometres from the nearest track using the helicopter, and on the way back to Yulara we were able to fly the length of this feature and actually confirm that that did reflect a surface rupture, a scarp. So that's looking at about 3 kilometres long of scarp that's about 40 to 50 centimetres high, This is a left step in the fault with a extensional crack linking that. So we did have a fault scarp, so that's excellent news. Our next trick was to get back out there, and unfortunately this was a movie that is not working, but that was actually showing how that track had degraded over the June to Christmas 300 millimetres of rain that they got in the desert. So there were a lot of washouts and it was quite bumpy. But our logistic issue was to get 150 kilometres along this dirt track from Cartajuda and then 4 kilometres overland through the mulga scrub to the centre of the scarp, and then the idea was to walk out 10 kilometres to the southeast and back, and then 10 kilometres to northwest and back with the RTK and measure this thing. So day one, so same day as we flew the helicopter out, we ended up that day at the fault scarp. So happy times, we've now started pointing at fault scarps, which is the culmination of the life's work of an earthquake geologist. Pointing is still important as you go along. So this is the second day we were out there looking to the southeast. So nice kind of arcuate sort of thrust rupture nipping off into the distance, quite linear in some cases. 0.3 to 0.4 metres high at the interface where we were able to follow it there. The next, in the most case we were looking at vertical motion. There wasn't a lot of evidence of lateral motion like strike-slip movement, but in a couple of cases we were able to see that, like in this Camel Trail, slightly displaced to the right. This is an extensional crack in a left stepper over the fault, suggesting there is some lateral motion on that scarp as well. But mainly a thrust event as the focal mechanism of the earthquake suggested. The next day we walked out to the northwest, and much bigger scarp up there, up to 0.9 metres high, averaging roughly 0.8 metres high. A really impressive thing, given that like a few weeks before, this land surface up here was down at this, and this thing built at 3.3 kilometres a second. So it would have been really impressive for the camel. So this is one of the particularly impressive bits that we're able to map, which is an extensional step over on the structure. On the ground, if we zoom in, these fissures were amazing. 25 centimetre aperture, and the dirt has basically fallen into it. Craig's got an 8 metre tape measure there, which proved inadequate to the task. Like looking down into it at night with head torches, there was no bottom to this thing, it went down to the mohos. So, that was quite stunning to see in the desert, you don't see that too often. And note to self that I'll come back to later, a lot of places along this scarp there was myelinitic bedrock in the footwall and the hanging wall. There were no deposits on the footwall on this side of the scarp that suggest that there had been previous events and then that scarp had eroded into a colluvial mantle, and I'll come back to that. So day 4 was a fine sunny day. The previous days were rainy and fairly drizzly. So decided to actually test the hypothesis that we were in fact looking at a thrust fault scarp. Like we've been walking along it and that was our model, but you never know till you dig a hole. So I didn't go to the bit where it was 0.9 metres high because that would have been shifting too much dirt, so we picked a spot where it was 0.3 to 0.4 metres high and I dug a big hole. And fortunately there was a thrust fault in it, so that was a happy time. We actually do have a thrust fault rupture. That was dipping about 30 degrees to the northeast. And using fancy photogrammetry technique you can actually make a 3D model of that and look at it side on, even though the trench wall was quite thin and you couldn't get a camera down into it. So that was a snapshot of our earthquake rupture. And I have a OSL sample in train to try and work out the age of that faulted calcrete, which will tell us the time since a previous event on this fault. Day 5, we started off and it started raining. So we gave Craig a call back at GA and he said there was a 40 millimetre rain event coming through. So discretion being the better part of valour, we hightailed it out of there back to Yulara, and it was fortunate that we did, because these are our University of Melbourne collaborators, and it cost them $1,600 to be rescued from that particular bog. So that actually started off a series of rainfall events in the Central Desert that culminated in Christmas, there being a 200 millimetre rainfall event over a couple of days. So this whole place was saturated. We expected the scarp to have washed away. But we couldn't get out there, which was a bit of an issue too, because we needed to download the seismographs. So what did we learn on that trip? The rupture exploited Proterozoic myelinitic fabric, which linked down, we assumed, at depth with the Woodruff thrust. So it's a high-grade, highly strained fabric. The actual thrust scarp runs along the back of these. So these are in the footwall. They were sticking up out of the ground before the earthquake, and there's a little 15 centimetre high scarp here. So the rupture is exploiting this myelinitic fabric. In terms of the RTK GPS versus the INSAR, that was a bit disappointing. So we collected 1,250 RTK points, 106 scarp vertical separation estimates, and 14 scarp perpendicular traverses. You can see these little green dots are the vertical displacement estimates, and this is the INSAR deformation envelope. And you can see with the RTK we're not actually capturing the full deformation at the scarp front, so it's suggesting there is off-fault deformation that we're not capturing with the GPS. And that is a problem, because as I said before, the scaling relationships that we develop using these historic fault ruptures basically relate an earthquake magnitude with a height of a scarp or a length of a scarp, and then you get a prehistoric scarp and you say it's 20 kilometres long, 2 metres high, so it must have been a magnitude 6. But if our scarp height measurements aren't giving us the entire picture in terms of the deformation, then our calibrations are going to be wrong. So we had to think of some other way of getting a better estimate of the scarp deformation. And fortunately, just last year we had got a little unmanned aerial vehicle in the geohazards group. It's just a little Phantom 4 off the shelf, about $2,000. And it provided a potential for actually doing some high resolution mapping along the scarp. I might say that we could have flown the scarp with LiDAR, but given the remoteness of the location, it's going to be an incredibly expensive business. Plus, your normal resolution of LiDAR gives you a 1 metre DEM, and we're looking for a sub 10 centimetre DEM so that we can actually pick up the fine details of the deformation envelope. So this is the sort of thing that the drone can do with the software. So you can pre-program in a flight mission, which it goes back and forth taking photos, and then you use photogrammetry software to stitch those photos together to make a 3D point cloud, which then you can make into a digital surface model and an orthomosaic. And using that, we flew 10 missions, and these are the ortho photos overlaid over the INSAR. Flew 10 missions, 164 line kilometres and 4,700 photos in a couple of days, just in late September this year, when we were finally able to get back out there. And I'll show you some of the actual images that we can obtain from this drone imagery. So that's a 4 kilometre wide field of view. Each strip is about 500 metres wide, and it takes about, like this strip out here for instance, would have taken about 30 minutes to acquire, and then there's a lot more processing overhead. But it's quite quick to acquire. We're actually getting an excellent image of the surface rupture going through. So we actually have a record of what the scarp looked like a year after the event and after 300 millimetres of rain. So it's still there, it's still pretty impressive. It's a little bit degraded, and the main problem we had was there was a lot of vegetation over it now, so we ripped a few tyres trying to drive into there. But If we compare these DEMs, like sections through these DEMs, to the RTK data, we're actually getting a pretty good match. Like the blue dots here are RTK traverses, the black profile is DEM. So I'm pretty confident the DEM is giving us a quite good representation of the actual surface. So if we compare that to an INSAR traverse, the INSAR is much coarser resolution than we're able to get with the DEM, but you can see that this red line here is that section of the scarp in the INSAR, and we're actually capturing the deformation across the scarp that the INSAR is seeing. So we're seeing the full deformation envelope, but I might say that this section was taken where the ground was flat. So before the earthquake, it was a flat surface, and we're capturing the whole deformation. The thing with the INSAR is it's a DEM of difference. It has a before DEM and an after DEM, and you subtract those to get the deformation, whereas the DEMs I'm collecting with the drone are just an after DEM essentially. So if there's topography, then I might not know which bit was original topography and which bit's scarp. So I focus in on the bits that are flat. If we put that data up against the INSAR and the RTK, we can see in the western bit of the scarp, the DEMs are actually doing a very good job. And unfortunately, I haven't had a lot of time to process DEMs in this central section. Still out to the southeast of the scarp, we're missing a bit of deformation in the DEMs compared to the INSAR. And we'll have to put that down to, there's an element of folding happening that is kilometre wavelength rather than the couple of 100 metre wavelength we're picking up with the DEM. But we're starting to get a much better appreciation from these DEMs of the actual deformation envelope, because we don't have INSAR over every scarp. So these are giving us alternative measures of how much the deformation was in the case we don't have INSAR, like the 2012 and 13 Annabella events. We didn't have INSAR. We never found a scarp. There could have been one there, but we don't have that data. So now we have a toolkit that can pretty much get us an envelope of deformation, and we can much better calibrate our scaling relationships. Another good thing about the high resolution imagery that we're able to pick up from the drone was we can get an orthomosaic at the same time as we get the DEM. So to focus in on this extensional step over, this is a 3 centimetre horizontal resolution digital surface model, and I could zoom into it if I was in ER Mapper at the moment, but it's in frightfully impressive detail. You can see these big cracks are showing up in it, and the lurid detail of the thrust scarp elements are also showing up. And if you zoom in, this is the orthomosaic. This is where we camped underneath the only bush on the entire place. And you can see the extensional cracks linking thrust fault scarps. So we have an incredibly detailed record captured of this rupture in perpetuity now, and anyone can work on that into the future. A really good thing that this allows you to do is actually get a much better understanding of the kinematics of that rupture, in that these are the thrust elements on a rose plot, and these are the extensional elements, and you can put that on a strain ellipse to give you an idea that we're actually doing pretty well with that, the focal mechanism, that it is a thrust mechanism with a slight strike-slip component. And there's a lot more work for me to do in the future in that as I go through the terabyte or so of data I collected. And while the batteries are recharging on the drone, that gives me time to dig extra holes as well. That was probably the major issue we had, was recharging batteries out in the middle of the desert. But yeah, again, a thrust scarp. So while I was away this second time, Gary Gibson at the University of Melbourne had actually processed all the data from the seismographs that we'd downloaded and had generated a catalogue. And as I said before, we've got 0.2 kilometre uncertainty ellipses on these epicenters now, as opposed to 10 to 20 kilometres from our national network. He's located 140 events in this catalogue from magnitude -0.5 to 0.4. And this is my first attempt at animation, but it'll give you an idea of what that actually looks like in 3 dimensions. So there's the RTK measurements on the face of the scarp, and we'll zoom around so that we're looking along the scarp. And you can actually see that we have imaged the rupture plane, so that's an excellent result. And one of the reasons that we set the high resolution aftershock kit out there was to say what is the rupture plane, and that allows people like Simon McCluskey et al. At ANU to actually do a slip model or even a dynamic rupture model of that earthquake, so that we can even better understand how the surface scarp became twice as long as we expected and several times as high as we expected. We still have the outstanding question of what role, if any, is the Woodruff thrust playing in this event. The Woodruff thrust surface trace is about here. Now, we don't actually know what the dip of the Woodruff thrust locally is, but there's a seismic line 170 kilometres to the west that shows the Woodruff thrust as a 20-degree southwest dipping structure. If we zoom into that area, this is the main Woodruff thrust, which is probably a kilometre or more wide, but there are actually structures linking into that Woodruff thrust that are antithetic to it, that dip towards it. And that provides a nice analogue for potentially what's happening in our earthquake scenario. So if we go back and we use this 20-degree dip on the Woodruff thrust, we actually see that this rupture actually propagated straight through the western margin of the Woodruff thrust, which is a bit of a surprising result. I don't really have an explanation for why that would be at the moment, but the Woodruff thrust is probably quite a wide crustal suture at this stage, so it may be more than the kilometre wide width that I've put there. But you can see that there are actually some earthquakes associated with where you would put a 20-degree dipping Woodruff thrust as well, and below in this stressed area. So that's a model to start trying and understand why this earthquake happened where it did. And if we look at the aeromagnetic map, this is the surface rupture as mapped in, and it seems to be along a magnetic lineament that actually links into the Woodruff thrust at a corner, which is an ideal stress concentrator as well. And of course, as I said, these structures that the rupture are picking up, so the things we can see in the aeromagnetics are these highly stressed myelinites. So there's no explanation of why the rupture should penetrate through the Woodruff thrust, but we're getting an idea that the Woodruff thrust might be important in that it's there. Why would you localise an event to that area? And we can have a look at several precedent earthquakes in this area. This is the magnetics with gravity as the colour over the top, Woodruff thrust again, with a step across the moho. In 1987 we had an earthquake at Marriott Creek, magnitude about 6, it might have been a bit smaller, maybe 5.7, in the hanging wall of the Woodruff thrust again. 2012 we had the Ernabella earthquake within 5 kilometres of the Woodruff thrust, and then the year after we had one in the footwall of the Woodruff thrust, so you're actually activating both sides of the Woodruff thrust in those two events, and now we've had one penetrate straight through the Woodruff thrust. So I think over that distance of maybe 300 kilometres, we're starting to build a picture that even though the Woodruff thrust itself is not weak and is not failing, the stress that it is concentrating by virtue of the step across the moho, structures that were put in place from 400 to 1600 million years ago, are still influencing the location of seismicity in the Australian continent. So that's still to be worked up, but it's a startling coincidence if the Woodruff thrust isn't actually guiding that seismicity. And getting back to my note to self in terms of the bedrock on the footwall, this cartoon shows you what you might expect from recurrent large events on a reverse fault. Your first event comes, that degrades into a colluvial wedge over with time. Second event, your colluvial wedge gets bigger. So if you expect recurrent earthquakes on this structure, you would not expect bare rock in the footwall. So we didn't find any evidence in a couple of field campaigns out there to suggest that this event had ruptured in the recent geological past, and by recent geological past I'd probably extend that out to maybe 1 million years. So this, for all effects, is a one-off earthquake, and that poses a particular challenge for probabilistic seismic hazard assessment in that we generally adopt a plate margin paradigm whereby elastic strain accumulates on faults and then is released as large earthquakes periodically. Whereas here we have a large earthquake that appears to be a one-off. And in being a one-off, it's not a one-off. We've had 8 historic surface rupturing earthquakes in the Australian continent. They've all occurred in the cratonic western parts of Australia, and although researchers have looked for recurrence on these things by trenching, they've not found it. So all of these historic events, I could not have said there was an active fault there prior to that event. For instance, Tennant Creek. There was not evidence for a scarp or relief generation prior to the 1987, 1988 events. So is this the modus operandi that we're dealing with in at least cratonic Australia? Is recurrence a meaningful concept in an intraplate domain? Or are we releasing strain from a fossil pool of strain, for instance the Woodruff thrust, according to some transient perturbation or pulse of stress through the continent, maybe from the plate boundaries or fluid conditions somewhere. So these are the sort of questions that we're starting to grapple with in our seismic hazard assessment. So to go back to the plate margin paradigm that we build into our hazard assessments, we would expect these large earthquakes to be recurrent on faults, and if you look at a vertical displacement versus time history on a fault, you would expect a nice neat line like this. But if we look, and you make certain predictions that if you were to look at the GPS signal, for instance, you should be able to see that elastic strain accumulating. Now this is 10 to 20 years of GPS data from our national network, and I can't see a pattern in that. It may be that we haven't measured for long enough, that the strain accumulation is so slow that we need to measure for another 100 years before the signal emerges from the uncertainty. Or it may be that we do not have strain accumulation in the Australian continent, that we are releasing fossil strain. And they're the sort of, if I were to map out my next 10 years, this would be the question, because it's really very important in terms of how we deal with a seismic hazard assessment. Do we build in the faults with regular recurrence or not? And that 3 used to be a north scale, but so this is Eastern Australia. This is the Lake George fault just to the east of us. It has built 250 metres of relief in the last 4 million years, so it certainly has recurrence of large earthquakes of some sort. So that doesn't work compared to the cratons, what I've just said. But what does that recurrence look like? This is a vertical displacement versus time history on the Lake George fault, and you can fit that plate margin kind of recurrence model into an active period on this fault. So there's been 3 active periods in the last 4 million years, separated by periods where nothing has happened. And we got this out of the stratigraphic record with seismic traverses and drill hole data in Lake George. So we have a episodic model of deformation rather than a quasi-periodic model of deformation. So if we were to take an average through that, that would be the plate margin paradigm. The fault's going to go off on average at this slip rate. But we're finding that there are significant excursions from this average and bits in between where nothing's happening. So it's not hazardous if it's in a quiet time at the moment. And we've just started in our new National Seismic Hazard Assessment 18 to build in some of these conceptual models of intraplate faults into the hazard map so that we don't just play the plate margin paradigm and get it wrong. In Western Australia and in Eastern Australia, we've had to float maximum magnitude earthquakes like these 6s and above anywhere in the Australian continent to account for these one-off ruptures. And that's fairly unique in the world's seismic hazard community. The US do it in the central and eastern US, they do a kind of more embryonic form, but we're definitely getting into the forefront of the kind of cutting edge science of how to incorporate intraplate faulting into these what is statistical probabilistic seismic hazard assessment based on a plate margin paradigm. Now, do we have very slow strain accumulation versus no strain accumulation? One way to test that is to measure the GPSs for another 100 years and then come back to that. But there are many paleoscarps in the cratonic bits of Australia that also show multiple events, like they're 10 to 20 metres high. They might have half a dozen events or more. So they have some sort of recurrence, similar to, like George has some sort of recurrence. So the question is, are they very slow, or is there no strain accumulation and all those events are unloading a certain bit of crust all in the one time, or as a transient perturbation goes through the continent? And interestingly, my work on the Albany-Fraser and Euclid-Gawler seismic traverses suggests that the faults that have the accumulated throw are the ones that tend to be linked into other faults at depth. So this bottom map, the red lines are faults that you can see as surface fault scarps that link into the seismic data that go down through the crust in some cases. So it's not an intractable problem. We can actually access this problem of whether we do have slow accumulation or no accumulation, and the ideal place to do that is in one of these scarps. This is an Arabine scarp in southwest WA. You can see the sun is shining from the west, so the scarp is west side up, east side down, and you've had a little stream following down a paleo valley that has cut a, I say canyon because I've ramped up the vertical exaggeration there, but it's a broad valley that it's cut through there, and you can see that there are a few lakes as well. So this stream system and the lakes overlay a paleo valley that has probably an Eocene and a Pliocene, so tens of millions of year old of sedimentary fill. So by studying the longer deformation history of one of these faults, we can start to access the question of, is the deformation that we see at the surface now the only deformation that has ever occurred on that fault? Or does it have a protracted history of faulting over the last several million years? And that'll affect the models that we put into the seismic hazard assessment. And I'll be handing around a hat later if anyone wants donations to dig any holes in that fault. So I've kind of finished up a bit earlier than I expected to, but that'll give me time to go through a vast range of thanks for this work. I guess I was the one driving the field surveying, but there were a lot of people in the background that actually contributed to this data, in particular collaborators at the University of Melbourne and the ANU. But the GA people got the INSAR data working, and that ended up being gold, really, because ultimately we went to where the INSAR said there was a fault scarp and there was a fault scarp. So in the future, if there's one of these events, it'd be the INSAR I'm looking at to actually tell me where to go rather than us kicking around trying to find a fault scarp by accident. The University of Melbourne people went out there just before the INSAR data came out, and they walked 20 kilometres through the desert and didn't find the fault scarp because they just walked the wrong way. So the INSAR helped. And I think I'll leave it at that, pointing at the fault scarp.